Hello everyone, my name is Denitza Dramkin, and I'll be presenting some work done with my supervisor, Darko Odic, on how children map number words to their perceptual representations.
Children possess remarkably rich intuitions about the world, including the ability to rapidly make judgments about number, length, and area without needing to count or measure, such as when deciding which of two plates has more cookies, which churro is longer, or which piece of chocolate is bigger. And through development, children also learn to attach language, like number words, to these dimensions, allowing them to verbally quantify their intuitive, though imprecise, perceptual representations, such as being able to estimate that there are roughly 10 cookies on a plate, a churro is roughly 10 centimeters long, or that a piece of chocolate is roughly 10 centimeters squared big. But how do children ultimately accomplish this feat? In other words, how do children link number words to their perceptual representations? One possibility is that children must learn to map number words individually to each dimension based on independent associations. That is, they must learn to associate number words to number, to length, and to area, all independently of each other. And so, under an associative mapping account, children form links between number words and perceptual dimensions through forming item-specific associations, linking particular perceptual states to particular number words. And if this account explains how children link number words to number, length, and area, then these links would need to be established for each dimension. And so we would predict that despite maybe knowing how to verbally estimate in one dimension like number, children would not automatically be able to attach number words to other dimensions like length and area. Alternatively, linking number words to perceptual dimensions may act more like a simultaneous event, such that the very moment children can form a link between number words and one dimension like number, they can do so in others like length and area as well. Hence, a structure mapping account would predict that children could link number words to their perception by understanding the shared logic that underlies the interface. So, for example, if children understand that when they see that something is two times more, they respond with the number word two for one dimension, children could use the same logic to apply this to other dimensions as well, such as through analogy or an understanding of the shared ordinal or ratio structures, allowing children to readily map number words to their perceptual representations across different dimensions and units. And so, in contrast, a structure mapping account predicts that children's ability to map number words to one dimension allows them to readily extend their understanding of this link to others as well. And so, these two accounts make very different predictions about what should impact children's abilities to map number words to perceptual dimensions. When it comes to experience with particular dimensions and units, the associative mapping account predicts that familiarity would play a significant role in children's abilities to ultimately create links between number words and their perceptual representations, as they would need experience forming item-specific associations for each dimension and unit. But in contrast, a structure mapping account would predict that familiarity or experience with particular units and dimensions is not required, as the very moment children understand how to link number words to a particular unit in any dimension, they can extend this logic to other units and other dimensions as well. And when it comes to the quality of the underlying perceptual representations, if associative mapping underlies how children link number words to number, length, and area, then we should also expect that the quality of the link children have between number words and perception to depend on the quality of the underlying perceptual representations themselves, such that for dimensions where children are better able to perceive fine distinctions in quantity, they are also better able to precisely link number words to those representations. However, if how children create this link is more consistent with a structure mapping account, then we would predict that even if children do not have access to precise perceptual representations in a particular dimension, they could still generate links between number words and their perception of number, length, and area. And so to test these two competing accounts, we had 5 to 11-year-olds complete an estimation task. And we chose to start at age 5, given some previous work showing that this is when children first establish a mapping between number words and numeric quantities. And for the estimation task, children were rapidly shown displays and were asked to judge how many items they saw. And to control for experience children may have had with particular units, including units of measurement, we created novel units across dimensions, including one 3-dot unit called a toma for number, one 44 pixel long line called a blicket for length, and one 111 pixel square blob called a modi for area. And once children were shown these units and how to use them, they were subsequently shown more numerous displays of dots, longer lines, and bigger blobs, and asked to estimate how many tomas, blickets, and modis they saw across trials in an intermixed order, with the use of the quantifier how many and plural syntax, modis, guiding children to provide a number word estimate. And the target values were also kept consistent across each dimension, with the correct answer always being 5, 8, 13, or 21, tomas, blickets, or modis. Now, critically, if something like an associative mapping underlies the link between number words and perceptual representations, then we should actually predict that children will struggle in the verbal estimation task. So for example, if we were to plot children's verbal estimates on the y-axis against the target values on the x-axis, with the hollowed out circles here to indicate where perfect estimation performance would be, we would expect verbal estimation to look something like the following. For a number in yellow, we would predict their estimates to way overshoot the target values, because here 3 dots corresponded to a single unit for number. So even though the target values are still 5, 8, 13, and 21, the objective number of dots on the screen is actually represented by 15, 24, 39, and 63 dots. This would mean that any prior experiences and associative links children may have had with number estimation would not be consistent with the correct labels for these displays, as when shown something like 39 dots on the screen, the correct answer would be only 13 tomas. Additionally, our youngest participants would have had little to no formal experience estimating with length in orange and area in blue. And even if our older participants did have experience with estimating in these dimensions, we still gave them novel units. And so we should expect that children will really struggle to link number words to these dimensions, demonstrating flat performance across target values. Because under an associative account, children simply would not have acquired the link between number words and these dimensions and units. But in contrast, if something like structure mapping underlies the link, then if we were to again plot average estimates against target values, with again perfect estimates indicated by the hollowed out circles, we should expect to see something more like this, whereby children are able to demonstrate higher estimates for higher target values across dimensions, with there maybe being some level of noise or individual differences in each dimension. And so these two accounts make very different predictions about what we should see in children's verbal estimation. The associative mapping account predicts that children will actually not be able to do this task, given that they wouldn't have formed item-specific links for these unfamiliar units and dimensions. While the structure mapping account predicts that children will be able to rapidly form links between number words and novel units and dimensions because they understand the logic underlying the interface between number words and their perceptual representations. Okay, so what did children do? Here, I will plot children's average estimates with the mean estimates on the y-axis and the objective target values 5, 8, 13, 21 shown on the x-axis. And again, the hollowed out circles are used to help visually indicate where a perfect estimate would fall. And when we look at performance across number, length, and area, we find that children generally underestimated across dimensions, which is typical for estimation tasks. But critically, we also see that they gave higher estimates for higher target values. This importantly suggests that they were able to generate a mapping for these units, even for dimensions like length and area, which our youngest participants had little to no formal experience with, which is pretty impressive. But what I also want to draw your attention to is their estimates for a number, because here we see that children also appeared to be able to map a 3-dot toma to a single unit for number. and that they were not just responding with the brute number of dots on the screen. This is actually even more remarkable considering that if children did have strong associative links, such as the association between the word one and one item, then they would have had to inhibit these competing links in order to succeed in this task. And when we look at the data, once again, plotting the average estimates across target values, but this time distributed across age groups, we see that for number, length, and area, children showed positive slopes across dimensions, with average estimates increasing with target values in each age group. And so we see that despite limited or no experience with particular dimensions or units, children as young as 5 could map number words to their perceptual representations, even mapping 3 dots to 1 toma, which is even more remarkable considering that our youngest participants hadn't yet learned how to formally multiply or divide. And so, on the one hand, it seems that we have evidence for a structure mapping account because children could verbally estimate across dimensions and novel units, demonstrated by them consistently providing higher estimates for higher target values. But at the same time, we also see a bit of differences in children's estimates for each dimension. And recall that according to an associative mapping account, we should expect that the quality of children's link to number words will depend on the quality of the underlying perceptual representations themselves, such that for dimensions that children are better able to perceive, find distinctions in, they are better able to establish precise link to number words. So what this means is that if children were actually somehow able to verbally estimate through associative mappings in our tasks, maybe because they had existing links from our practice dimensions like number, then we should find that for dimensions where they have the best estimation performance, they also show the best perceptual sensitivity. And so to test this, we had the same participants, again 5 to 11-year-olds, complete a perceptual sensitivity task. And for this task, displays of dots, lines, and blobs were quickly flashed on the computer screen, and children were asked to judge which side of the screen appeared more numerous across intermixed trials. For number, when judging which side had more dots, which line is longer for length, or which blob is bigger for area. And to vary difficulty, each trial varied in one of 4 ratios, and accuracy, or the percentage of trials in which children correctly identified the more numerous side of the screen, was used as a measure of differences in children's underlying perceptual representations, with higher accuracy indicating greater perceptual sensitivity. And so on the y-axis is the accuracy or percent correct, with higher values indicating greater perceptual sensitivity, with the x-axis corresponding to performance on number, length, and area trials. And as we can see, children were significantly more accurate on length and area trials compared to number, suggesting that number perception is worse than these other domains. And so, if underlying perceptual sensitivity can explain how well children are then able to link number words to their perceptual representations, then we should see verbal estimation for dimensions like length and area to be far better than number based on these results. And so, we'll look at the estimation performance from earlier in more depth. And one way in which we can do this is to look at estimation accuracy, or how close the estimates children gave were to the objective true value shown. So for example, if we take the same plot from earlier with average estimates plotted against target values and hollowed out circles representing where perfect estimates would fall, let's say that these are the estimates a participant gave for some dimension. And so to get a measure of estimation accuracy, we can take the absolute average error rate, or AER, which is the absolute average percent difference between the true objective value shown and the estimate provided by children. And we chose to take the absolute average error rates because we weren't concerned with the direction, but rather the overall degree of under or overestimation. Hence, AERs closer to 0 would indicate a more accurate link between number words and children's perceptual representations. However, it's important to also consider that children are shown the same target values repeatedly across trials, meaning that for every target they estimate it several times. And so in order to capture the variability of their estimates, which can be very different across different ranges of responses, we calculated each child's average coefficient of variation, or CV, or the standard deviation for the estimates divided by the mean, with values closer to 0 indicating less variable and thus better estimates. Hence, what we should expect is that if children are good estimators, they will show lower AERs, indicating less under or overestimation, and lower CVs, indicating less variable estimates for dimensions that they are better at estimating in. Okay, so I'll first highlight estimation accuracy, or the mean absolute average error rate, or AER, of children's estimates, with the mean AER shown on the y-axis and performance in each dimension represented on the x-axis. And as a reminder, lower values indicate better performance. And when we look at estimation accuracy for number, length, and area, we first see that their AERs are pretty low, even relative to some previous work on adult estimation. But we also see a very different pattern compared to the perceptual sensitivity task, with number estimation being far more accurate than area and roughly equal to that of length. Hence, despite demonstrating far greater perceptual sensitivity for length and area, number estimation was far more accurate than area and roughly equal to that of length. But what about the variability of children's estimates? So here we plot the mean coefficient of variation, or CB, on the y-axis as a measure of variability, with each dimension once again represented on the x-axis. And as with estimation accuracy, lower values here are better, as this indicates less variable estimates. And when we look at the results for number, length, and area, we see that children's estimates have rather low variability, but with number estimates being far less variable compared to that of length and area, as indicated by the lower mean CV values. And so together, we see that children's estimates for dimensions like area are far less precise and more variable than dimensions like number. And so importantly, this demonstrates that underlying perceptual differences do not account for verbal estimation performance, since despite number perception being the worst, children were way better at interfacing number words with their perception of number, especially when compared to area, and despite being given completely novel units for number too. And so we started off with this question of how do children link number words to their perceptual representations across dimensions like number, length, and area. And we asked whether children must learn to map number words to these dimensions independently, such that knowing that there are roughly 10 dots does not automatically mean that children can judge roughly how long a line is or roughly how big a blob is, or if instead this link actually occurs more like a simultaneous event, whereby once children can link number words to one dimension, they can use the underlying logic of this link to map number words to other dimensions as well. Together, our findings suggest that this link between number words and intuitive perceptual dimensions is a major developmental achievement, as once children can link number words to one perceptual dimension, they can easily map number words to others. This is evidenced not only by children's abilities to estimate using novel units and across unfamiliar dimensions, but that any differences in children's underlying perceptual abilities did not account for the quality of the interface with number words, as despite demonstrating better perceptual acuity for length and area, children were relatively worse in length and area estimation, even though the target values for number words were identical across dimensions. And finally, and most impressively, children were able to map number words not only to dimensions that they had little to no experience with, but they were also able to map number words to novel number units, which is even more remarkable considering that children had potentially competing links that had to be inhibited, and that our youngest participants had not yet learned how to formally multiply or divide. This further demonstrates that children could readily and easily map number words to units and dimensions that they have little to no prior experience with, suggesting that mechanisms akin to structure mapping must underlie at least part of the link between number words and perceptual dimensions. And so with that, I'll say thank you, and I look forward to your questions.